Okay, let's get started, guys. So in the previous class we were doing deflections by method of virtual work. Okay, our main focus was on the principle of virtual forces. As I told you that there is another principle also, which is principle of virtual displacements, but that one we are not doing. We are just covering the principle of virtual force. Now, we said that in this principle, what happens is that we have got one real system and one virtual system. Okay, we take a static part of a virtual system, multiply that with the kinematic part of a real system, yeah, and find the work done. Okay, or in other words, apply the energy principle. What is the energy principle? The total energy remains the same. External work is equal to internal work. Whatever energy goes in the system comes out of the system. Okay, so it's that. So the principle of energy, or you can say that the total energy, that principle is used but in a slightly different way. Why? Because we are not talking about one system. Okay, we are not talking about one system where you apply the load and you get the displacements. We are taking the applied load system of one system and comparing that with another system, which is a virtual system. Okay, find the work done of that virtual system. So in other words, we are mixing two systems and applying the internal work is equal to external work on it. Okay, so that is the main theme of this principle, and that's why the name goes virtual work method. Now So we have the energy principle. It's also called first law of thermodynamics, which is the energy input is equal to energy output. Or in other words, whatever energy goes inside will come outside, or external work is equal to internal work. External work is the energy which you are pumping in. Internal work is that energy which the system is consuming in such a way, and as a result it is coming out, it is deforming, or I mean like some it might go crack, I mean like it might fracture or whatever, but that energy is consumed in such a way. So the bar denotes virtual system. In the virtual, so we have these ones. The load and the corresponding moment. That is the virtual system. And we have the displacement, or the displacement profile, or the deflection profile, you can call it, related to the curvature. Related to the curvature, and that is your kinematic system, which is the real system. Okay, that is the real system. Now, in the previous class, we applied this principle on a truss, simple truss system. Today, we will try to apply this on a beam and a frame. Okay, so that's what our aim is. So let us see what happens if we apply this system on the on a beam first. Remember that the main idea, the main thing which we are after, the objective is to find out the deflection, okay, deflection of the system. So let us have a problem. May I ask you to reduce my Okay, so this is the problem. A simple cantilever beam, and we are asked to find out deflection at point B. Okay, so that's what our aim is now. Now, how do we apply the principle of virtual work on it? First of all, we have to establish where should the load be applied in the virtual system. Okay, so in the virtual system, the load will be applied whereabouts? At B, because we are interested in finding out the deflection at B. So this is so let us draw the bending moment diagram for this one, shall we? So this is 12 kilonewton per meter. How much this is going to be? 12 into 10 into 5. Please, how much is that? 600. because we should draw M over EI diagrams. Okay. Now, let us write this equation being tailored into your beam problem. Okay, so let us adapt this to the beam problem. What should we do? This is the external work. This is the internal work. What did we say? The external work is equal to 1 time delta B. Can we write that? Why? Why can we write that? 1 times delta B, there is an integral. Why is that? Why just 1 time delta B? Yeah, force is, the external force is 1 kilonewton, isn't it? Yeah? If this was a UDL, so yes, then we would have multiplied it with the full deflected profile. The deflected profile of this one is like this, isn't it? So this is the deflected profile. We are taking this load and multiplying that with the deflected profile. Okay? The reason we have taken 1 kilonewton, you know, is actually to break down this integral. So this integral is squeezed into just 1 point. Do you understand my point? Why have we taken 1 point? Why? Because this is, if there were a series or a train of 1 kilonewton, then you would have multiplied each corresponding load with the displacements, okay, of the real system. So in current case, we have just one load, so 1 times delta B. Okay, is that clear? Yes. Okay. So 1 times delta B is equal to yeah. So now this is 10 meter. Okay. So this tells me that this is 0 to 10. Agreed? Yes. Okay. Now the thing is, we have to take x. Okay, why? Because this is a varying load. It's a varying load. It's a it's a distributed load, and for a distributed load, and we have to multiply that with m of x multiplied by k of x. In other words, our moment is a function of x. We don't have a choice. We can't do this sort of thing in here. Why? Because the moment is always a function of x. It's a continuous function. Okay, moment is a continuous function, and similarly the curvature. Okay, the curvature. So moment is moment of the virtual system, which is this one. Okay, and we have to do it in the form of x, isn't it? You remember in your previous in your old classes or in your previous term when you were when you would be asked to find out the bending, to draw the bending moment diagram or find out the bending moment. Okay, so you would work out the general bending moment equation, isn't it? M of x. And why would you determine it in terms of x? Because moment is varying along the length. Yeah, that's why. It's not just specific to a point. Okay, it is varying all along the length. So that's why. So similar thing is true over here. Moment is varying. Okay, along the x. Now the problem is, where should we take our x? So you have to be a bit strategic in taking your x. What do we mean by strategic? We mean that we have to reduce our labor effort. Okay, so that we have to simplify our integration. Okay, we don't want too many terms to be in the integration because there is always a possibility of a mistake, isn't it? So where should we take our x? Should you take it? You have got two choices, either from this side or from that side. From the left, why?
Because we have load here 1 times x.
Yeah, that's what we have got, just one load. If we take it from here, we will have a reaction and a moment. So we will have 3 loads. So there would be three terms in the equation. Yeah. From the right side, there is just 1 term. So that makes our life easier. So we should take our x from here. for the virtual system, 1 time x, okay, and it is above, so we call it, like tension is on the top fiber, so we can call it negative. Okay, so minus 1 times x, that is our m bar, okay, agreed? Times. Now what is curvature? What did we say? What is the curvature in the previous class? Curvature is equal to 1 by rho is equal to m over ei, isn't it? So that is the actual moment. So we have to multiply that with the actual moment. So the actual moment is this one. So that will come out to be minus 12x into minus 12x. Yeah. Divided by EI. Yes?
Yes, sir. On the tension side, moment is positive.
Sorry?
We will take positive moment on the tension side.
No, I'm saying that because this load is causing tension on the upside, on the top part. Okay? So that's why I've taken it negative.
If you write the temperature there, if you take the tension on positive on the upper side.
Yeah, so take it positive then, it doesn't matter. Okay? So
can you repeat this minus 12x step?
sorry, this one minus 12x is minus 12x is, this is 12, isn't it? 12 times x and 12 times x and x by 2. Times x into x by 2. That is my moment equation. So, minus 6x squared, and so this is 6x cubed. And then dx so what is it? What should I do to convert it into meters? What should I do? Then, so what I can do is
gigapascal, so it's 10 to the power 9.
Sorry?
The giga is 10 to the power 9. 200.
Yes, it is 10 raised to the power 9. But why have I taken 10 to the power 6? Because load is in kilonewton. So that kilonewton will cancel with kilonewton. Sorry? This is 10 power 0.99. So the deflection comes out to be 0.15 meter. Okay, is that fine?
Then, can you please tell me that whether it was left hand side?
Which left hand side?
Like we have done 1 into deflection and the one for lunar there is
In this formula, there is virtual load times the actual displacement. The virtual load is applied only at one point. Okay? And the displacement, Vx, yeah, that is the real displacement, which is actually the equation of this displacement profile. So 1 times this and the rest is 0, so all of them become 0. So you get just 1 times this delta, which is delta.
Sir, we don't have to deal with that integration.
So in the integration, you have 1 times this one. What is integration? You have got this thing, load times this displacement profile. So this displacement profile is continuous, but you have got just one load and 0, 0. So you multiply each of them 1 times this, and over here, yeah, then it's 0. So 0 times this, 0 times, so everything becomes 0. So you add it up, you get just 1 times delta V. You understand? So it's only in this integration, which is along the whole length, it's only this times this which is active. Okay, the rest is all 0. And okay, so in this question we have assumed, why have we taken minus? Because we have assumed that R we have assumed this as positive, isn't it? In other words, we have assumed this as positive, which is our normal sign convention. But this comes out to be negative, that's why it is in this direction. And it has come out to be positive. The deflection has come out to be positive. So what does that mean? The deflection must correlate with your moments. So your moment is like this, isn't it? This profile, what we are doing is we have left it like this. Okay, that's how. And then it moves like this. Do you understand my point? This is my cantilever. I move it down. So what am I doing? Essentially, I've got moment in this direction, but this has moved down. Yeah, and the deflection is also like this. This has moved down. So it's not like it has moved up. If it had moved up, that would have been like this. So a moment in this direction. Okay? Are you getting the mind map or not? I'm saying, look, this is our profile. Okay? According to our sign convention, this is positive. This one is positive, isn't it? So, according to our sign convention, this is a positive profile. Okay? Sagging. Sagging is the positive. Yes? Now, if this sagging one, if this come down like this, so that is my positive deflection. Okay? Initially it was like this and now it has moved like this. This is my positive deflection. Okay? Now, what is happening over here? It is actually like this. Yeah, and it has come down like this. So the deflection, so that's why the deflection is consistent with your moment, with your moment profile. Do you understand my point or not? Are you guys with me or not? Please
Yes, sir. Yes, sir.
speak up. Look, the moment, profile and deflection, they must be agreeing with one another. That's what my point is. The moment, distribution and the deflection, they must be agreeing with one another. Okay? So, when we have, this is our positive moment, this is our positive moment. Okay? So, in other words, hogging is our positive. Okay, so the deflection is, if you have a beam which hogs like this deflection is positive. Okay, why? Because the deflection and the moment, they are in the same direction. Agreed? In this case, what happens? It will come out to be, if your deflection is positive, that means that it is consistent with whatever you have with your moment direction. Okay, so in this case we have got this sort of situation, isn't it? Look, I've got moment applied over here, so we have got hogging situation. So that hogging situation has, what has happened? This end has slightly come down like this, but it still stays hogging. So the deflection come out to be positive. That means that whatever we have considered over here, that it is negative hogging, that is okay. Do you understand my point? So your deflection and moment, they should be consistent with one another. It doesn't mean that 0.15 means that it is moving up. If it is moving up, then that means that you are considering how can it move up. Okay? That means that you will have a hogging mode, a sagging mode. It can only move up in sagging, isn't it? Yeah, so that's not true. So if this had come out to be negative, that would have meant that you have sagging moment, yeah, and this would have moved up. So that's what I'm saying. Is that clear? So you have to correlate your moment and your deflection all the time. It's all this similar to what we did in conjugate. Okay, any question? Shall we rub it off? Okay, we'll rub it off. I'll stop it.